Expected value is an interesting topic in probability that examines, if there are certain outcomes for different events, what's the predicted outcome? So let's look at a simple example. Let's imagine that we have some die, so a six-sided die, where in this six-sided die, each outcome has an equal likelihood of happening. So we're just as likely to get a 1 as we are to get a 2, as we are to get a 5, and all the other numbers. And let's say that there's some game where here is what you got on your roll. So on your roll you can get a 1, 2, 3, 4, 5, or 6, and then there's some outcome. So let's imagine some sort of, I'm not saying that you should go to a casino. In fact, do not. You're not allowed. But let's imagine some casino game where if you rolled a 1, you got $1. And if you rolled a 2, 3, or 4, let's say you got $2. So we're just creating some arbitrary game. And let's say if you got a 5, you lose $1, so -1. And if you roll a 6, you get $20. So if you were to play this game many, many times, many, 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 many times, so letting the law of large numbers come into play. And by that, the law of large numbers is saying that as long as you do something enough times, so in the order of thousands of times, if you do something enough times, what you would predict because of probabilities will start to show up. So the expected value, which we will for now write as EV, where is that expected value going to come from? Well, one way to kind of think about this is imagine if we had, let's say, like 6 million rolls. And I'm choosing 6 million rolls because it's enough rolls that the probabilistic model will start to be true, or in other words, we'll get the outcomes that we would expect. So let's just suppose that we had 6 million rolls. Well, if we had 6 million rolls, roughly, we're going to get 1 million rolls of each number. Now, will it be exact? No, but close enough. So, and we'll write that as times 10 to the 6th, or maybe even simpler as 1e6. So I'm going to roll a 1, a 2, a 3, a 4, a 5, a 6. Each one of those I'm going to roll roughly 1 million times if I roll 6 million times. Therefore, I could think about my payout. Well, my payout is just the outcomes times the number of times I get that outcome. So I'd have 1 million. I'd get $1 million from rolling 1 million ones. I would get $2 million from rolling 1 million twos, because I get $2 per. I'd also get $2 million for rolling 1 million threes, and $2 million for rolling 1 million fours. I would lose $1 million for rolling 1 million fives, and I would gain $6 million for 1 million sixes. Okay, so then the total earnings that I would get if I just add those up would be 12 million. Well, I'd get $12 million over 6 million rolls. So what would that mean? Well, that would mean that I'm roughly getting $2 for every roll. Just dividing 12 million by 6 million, and my units are dollars per roll. So that would say on average I get $2 per roll. Well, what's a cleverer way of doing that? So what we could do instead is think about, well, what's the probability of each one of these events happening? So since there's an equal likelihood of rolling a 1 through 6, the probability of doing each of those is just 1/6. And therefore, there's a, kind of going down this column, there's a 1/6 chance that I'm going to get $1 by rolling a 1. Similarly, there's a 1/6 chance that I'm going to get $2 by rolling a 2. And I'm actually going to have 1/6 times 2 3 times. So I could just multiply that all by 3, since there are 3 ways where I can win $2 with a probability of 1/6. Okay, and then there is a 1/6 probability that I lose $1, so that's -1. And there's a 1/6 probability that I get $6. And if I do all this out, I've got 1/6 plus 1 minus 1/6 plus 1. This equals $2. Cool. It's the exact same thing as before. So therefore, we are onto a really nice way of thinking about expected value. So what we can say is that our expected value is the sum, and this is a new notation, and we'll talk about this later, but we could say it's the sum of all the probabilities multiplied by their outcomes. And this sum, this right here is the sigma notation, and it operates just like the pi notation, but it just adds things up. So we're going to go from I equals 1 to I equals I. Well, since we haven't really talked too much about sigma notation, let's write this a slightly different way. Expected value is just the probability of one thing times its outcome plus the probability of another thing multiplied by its outcome plus the probability of a third thing, if there are 3 things, times its outcome plus ... the probability of the nth thing times its outcome. Interesting. This will be helpful as we develop our casino games.